Okay, so bisection method. I might have mentioned this in the root finding methods, but I don't remember 100%. So if you recall the intermediate value theorem, which was on your last exam, well, I'm not going to state this in full, but we had an application of the intermediate value theorem, which is very useful to recall for bisection method. So, so intermediate value theorem, specific case. If f of x is a continuous function, continuous on some interval a to b, I guess it technically, extreme value theorem, we have to include the endpoints. I guess for continuity, we don't have to. Right, we wouldn't have to. Okay. Oh, but it needs to be defined on A and B. Okay. So if it's continuous on this interval, if f of A and f of B exist, and one of them is positive, the other is negative, then f of x has a root in AB. So the reason I'm restating this is because, unlike with Newton's method, which is only uses one point, it's very different. With bisection method, we are going to start with 2 points surrounding our zero of our function, and we have to have one of those points have f evaluate to a negative number and the other one to a positive number. And then we use that to kind of close in on the root. So we, as long as we're staying positive, we keep moving the top one down. As long as we're staying negative, we keep moving the bottom one up towards the root. So in particular, visually, first of all, how this works. And please tell me if I go off the screen at all. Oh, okay. That's not part of your graph, that's the end of my screen. Okay, so visually, what this will look like is, say we have a function, maybe here's a, we'll say a is like -1 and b is 3, for example. What we're going to do, and the reason it's called bisection is because at every step, we're going to cut the interval in half. And if the new point in the middle of the interval is negative, we move A towards that to be that new point. And if it's positive, we move B to be that new point. So we'll actually call this A1 and B1. When you're programming, you'll just call it A and B because you'll just keep resetting these variables. But when we're talking about it on pen and paper, we'll call it A1 and B1. And then since this is an interval of length 4, we're going to cut it in half. So that brings us here. Right, the middle of the interval is this point, P equals 1, or P1 equals 1. And so what we do is at that point, we ask ourselves, is the function positive or negative? And since the function is negative at that point, we take our A value and we move it and we reassign it to be this P value. So instead of A1 being -1, we're going to get our next value A2 to be 1. So we've moved A because A corresponds, in this case, to the negative value, only because the negative value is on the left. And then this B1 for the next iteration becomes B2, but it doesn't change. So we're only changing corresponding to the sign. So then we chop our interval in half again. And then at this next step, so this is P2, which is 2. 2 is obviously our value right between 1 and 3. So when we have P2 equals 2, the function's positive. So we move our B closer this time, not our A. So what happens now, and I'll write this below here instead, is that B3 on our third iteration becomes this value 2, and then the A doesn't change in this case. And then we continue this process. So then here, B3, or P is 1.5 in this case, because we're going right between 1 and 2. And we can see that 1.5 again corresponds to a positive value of the function. So we'll say B4 is 1.5 now, because we moved the B because the function is positive, and then A4 stays the same. So we're just zeroing in on the 0, I guess. And what we want to do is repeat this not until we have an error in the sense where we check the actual value against our estimate, but we know our error is small when our interval around the 0 becomes small. So realistically, when we've been checking error in the past, we've been computing the actual value, and we've been comparing our estimate with the actual value. That doesn't realistically make sense when you're trying to estimate a value. You don't know the actual value. So something like the bisection method, we know the error is small when the interval is small. So in this case, say we stopped here. So if we stopped here, our guess for the roots will be R equals 1.25. So when we guess the root, we don't pick A or B, we pick the point in between A and B. Because we know the root's somewhere in the middle of there. We don't know that it's directly in the middle, but if we pick the point right in the middle, then what we know is that the error, if our guess is 1.25, and we know the root's between 1 and 1.5, then our error is no larger than the half interval. So the error in this case, and when I say error without specifying, I'm always talking about absolute error. So the error in this case is less than or equal to 0.25. So that's half the length of the interval. So the bisection method, the power, I guess, behind the bisection method, and the reason why it's one of the important methods is not because it's fast. It's not that fast. It is like log time because we're cutting the interval in half every time. So it's not that slow either. But it converges much more slowly than something like Newton's method. But with this method, we are guaranteed to get our root. Like we know that the 0 exists between our interval. We're always getting closer and closer. We're guaranteed to get our root. We're guaranteed to get a really straightforward bound for the error. And so it's nice in that way. And sometimes you need to, guarantee that you're going to get a certain solution. So the bisection method is helpful there. So I'll go through like this algorithmically, like what you would actually want to code for this, or how to think about this process if you're writing it down mathematically. But before that, are there any clarifying questions? Okay. Please do interrupt if you have questions as well. And the other thing I will say about this is realistically, if you watched the Intro to Root Finding Methods video, you saw that something like Wolfram Alpha uses a root finding method in order to solve certain equations. So realistically, if you're using a computer algorithm to solve certain things, you're not necessarily going to straight up use like the bisection method. But what you'll do is often, or what will be programmed frequently, is sometimes some like interplay between different root finding methods. Like Wolfram Alpha might say, oh, this one root might be a little hard to make sure we converge to using this other more advanced method. So we're going to, get closer to the root using one method, and then we'll pull in a different method when we get close to the root to get a really good estimate quickly or something. So really with all of these methods, though, we're going to do them as individual methods. The way they can be implemented is often with an interplay between a combination of the methods in order to get speed and accuracy. Bisection method is about accuracy. Newton's method is about speed. So there are ways to make both of those work together for you. Okay, so anyway, the bisection method, step by step how it works is, well, first you start with an interval. So we start with an interval A1, B1, with f of A1 and f of B1 have different signs. Therefore, we know there's a root in that interval. It could mean that there's two roots in the interval, so things could go haywire. But if you're using bisection method, you do want to try to start with an A1 and a B1 that just contain one root. I mean, so realistically, okay, I could have done a bad example here where my graph went back up and then back down. And then my A1 still would have had a negative value. My B1 still would have had a positive value at the function. But you don't want to put yourself into a situation like this where you have multiple roots in the interval, because usually you're trying to find a specific root or specific solution to your equation. Or maybe you want all of them, but you do one at a time. So you do want to be a little bit careful, but most of these things you can usually kind of estimate. You can say, oh, well, I know the other root is going to be somewhere further down the number line, so I'll just use A1 and pick your A1 wisely and your B1 wisely so that you're only containing one root. Okay, so we start with A1, B1 with different signs. And then the second step was to calculate the midpoint of the interval. So calculate, I'll call it PI equals AI plus BI over 2. So we calculate our midpoint of the interval. This is kind of the obvious way to calculate a midpoint in terms of, if you know you want to get a midpoint, you just average the 2 points. And something like this, it's going to work just fine because our midpoints were easy. They were, whole numbers for the first 2 steps. But if you wanted to, you could calculate your midpoint this way as well. AI plus BI minus AI over 2. This gives you the exact same value if you simplified it. But the reason that this is sometimes recommended is because there's less rounding error in this case than there is in this case. Not always, but if there is going to be rounding error, this one tends to have less rounding error. So I'm putting it out there as something you should know, be aware of rounding error. But in the case of bisection method, if you do get rounding error, it usually doesn't negatively impact anything until you get really, really close to the root anyway. Because, if you're starting with an initial step, but you're still really far away from the root, then you don't care if your rounding error gets you off by 0.0001. All you care about is that you still have a point A on one side of the root, B on the other side of the root. One's negative, one's positive. So rounding error can become a problem when you're really close to the root, but in this case, there is no propagation of error, where at each step, you're kind of resetting the whole process where you have a new interval and then you're dividing it in half. So in that sense, we're not as worried about rounding error with something like bisection method, because there's no rules about what A and B have to be. We just have to have one on each side of the root whenever they are. So this is maybe useful, but I usually just choose to do this unless you're doing something really finicky and trying to get really close to the root. But at that point, usually you're on Newton's method or something quicker to get a good estimate anyway. Okay, step 2, calculate the midpoint. Step 3, remember we reassigned either A or B depending on whether the midpoint had the same sign of f of A or as f of B. So step 3 is if f of A, step 3 is actually, this is important, calculate f of pi if f of pi is 0, return pi as the root with little to no error. Okay. So you always have to check for this because, if I check just for negative and positive, then my if statement's going to kind of blow up in my face if I actually got to a situation where I did find the root in the middle of the interval. So the first thing you do need to check is at every step you need to make sure that if you get 0, then that's your root. I say you return it as your root with little to no error, and that's just because maybe your computer thinks it's 0 because of rounding or truncation error. But in that case, the error is still small if you're going out to enough digits for your computer to think that f of pi is 0. So I can't technically say no error because there could be a rounding error thing happening, but you can still return it as your root because obviously you're not going to get better than your computer's precision anyway. So once you have that, then you end, obviously, if you found the root. Otherwise, so else, if f of p1 and f of a1 have the same sign, what you're going to do is set A2. Oh, sorry. Let's make this PI, AI. We can be more general. We don't have to do A1, P1. We can set AI plus 1 equal to whatever our pi was, because we're moving the a if it has the same sign. And bi plus 1 is just whatever bi was. I'm almost off the screen there. So the a moves, the b doesn't. Otherwise, f of pi and f of bi will have the same sign. So, but I'm not going to write that out. I'll just say otherwise, which leaves that one case. Bi plus 1 gets moved to what our pi was, and ai plus 1 doesn't move, it just stays the same ai as before. So then you go ahead and you repeat this process. So repeat until the midpoint of the interval, ai, I don't like using, oh, well, I'll just use ai plus bi over 2. So obviously when I say repeat, I mean repeat steps 2 through 4. I'll write that here, steps 2 through 4. Obviously you're not going to reset your A1 and B1 every time through the loop. Repeat until this is less than your error tolerance. I think I put it in this lab. Maybe I didn't, but I think I did. Maybe it's in the next lab. TOL is what we're going to use often for our variable name that expresses our error tolerance. So we want the error to be below 0.0001 or something, then TOL will be our error tolerance. So we keep repeating until our midpoint is below our error tolerance. And our guess, our estimate for the root is this point exactly. So return AI plus BI minus AI over 2. You'll notice that in that last step, I did the less rounding error option because that's the only place where it matters as much. So yeah, we would return that, and then that would be our midpoint for the bisection method. Questions? Okay, let's do an example then. I'm gonna have to erase this. Is everyone done writing? Okay. So obviously with an example on the board, we can't get anywhere near the level of precision that we would want to get with a computer. I mean, we could, but that would be really annoying. So I'm going to do an example out by hand, but you know, only to like a moderate precision. So let's start with our function being, sorry, all my chalk is tiny. Okay, so let's start with our function being f of x equals x cubed minus x squared plus 4. And we're going to look for the root of this. That's like, oh, okay. Yeah, so I actually don't know. I graphed this and I just graphed it locally. So I have the part of the function with this root, but I don't know if it has 3 roots or if it just has 1 root. Because with a cubic, you can end up with either situation. And that is actually a lie. You always have 3 roots, but 2 of them might be imaginary, in which case you won't see them on a real graph anyway. So if you factored it in something like Sage, you would probably get 2 roots, or you might get 2 roots that have all these i's in them and stuff. and you can just ignore those because those aren't going to show up on your real graph. But cubics are nice to use for something like this, in part because we don't have a nice way to solve a cubic. We don't have something like the quadratic equation. Yeah. Is there a cubic equation? Is there a cubic equation? Someone Google that and double check if there's a cubic equation. I just don't want to give you wrong information. There's a degree 4 equation. Is there an all-purpose way to factor cubics? Okay, sorry. I have to look on the Google unless someone finds first. Cubic equation. Okay. Oh, okay. Okay, that's a relationship. Huh. Okay, I think the answer is no then, because it would be like a, yeah, all out. Oh no. How do I make you big again? Okay. Come back. Come back, students. Get big. What the heck? Okay, now you're big again. Okay. Okay. I think there's not then, because I think there'd be a very direct equation. I know there's one for degree 4. Sorry, I just like have a problem with maybe a little too much like, oh, all the math has to be rigorous. So if I say something that might be wrong, I want to check it. But then I do make mistakes, as you guys know if you've been in my class. So anyway, I think there's probably no cubic equation. And where the heck are my notes? Here they are. Okay, so anyway, there's one root that I definitely graphed that we're definitely going to want to hone in on. And yeah, we'll go from there. So our function looks locally something like this, where I graphed it. We have 0, I have 0.5, 0, negative 0.5, negative 1, negative 1.5. And then it goes through 0 somewhere around here. Okay. Well, it doesn't look like it's screwing my head on, so maybe there's another. Anyway, in this case, so I'm going to start with maybe, not the most efficient guess, but we'll say A1 is negative 1.5 and B1 is 0.5. And these first few steps, I'll even go through without doing all of the calculations because we can see realistically what's going on in that case. So if A1 is here, B1 is here, then our midpoint of the interval is 0.5 or negative 0.5. The function is obviously still positive at that point, so we're going to move the A down, not the B. So in our second iteration, A2 is going to get moved to the midpoint of the interval, negative 0.5, and B2 stays the same. Told you I make mistakes. Okay, A1 stays the same. B2 gets moved to negative 0.5. I messed that up. The function was already positive at the B value, and the function is positive at the midpoint, so we're changing the B, not the A. So we've cut the interval in half, and now we have AB here. Then when we cut the interval in half again, that brings us to negative 1. So then we have our A and B here. And again, the function's still positive at our midpoint, so we're going to, again, just adjust our B and move our B over, because B is the one that corresponds to the positive value. So A3 still remains negative 1.5, and B3 moves to negative 1. Okay, so, instead of doing all the math out for that, those were the more obvious ones. And then from here, what we would have to do now is we would have to do the tedious part. So we're only going to do really one step of the tedious part. Or maybe we'll do two if we feel like it. So next, our P3, our midpoint between A3 and B3, is negative 1.25. So at this point, what we have to do is we have to figure out whether or not our function is positive or negative at that point, and it's not obvious, right? Like, it's probably positive, but it's not quite obvious what's happening there. So at this point, so if you're doing things out by hand, you wouldn't have to show work for these first few. You can just look at the graph, especially because they're very straightforward numbers. But once you get to something like this, if it's not as straightforward, and at some point it should become less straightforward, we have negative 1.25 cubed, and then minus negative 1.25 squared, so minus 1.25 squared, plus 4. Okay. And so I'm getting, 0.4, blah, blah, blah. And I on purpose only told you one decimal place because all we care about is whether it's negative or positive. We don't care about, if we've made any rounding errors, as long as we know that it's firmly negative or positive. And if we're at 0.4 something, positive 0.4 something, then we know that the value of the function is positive there. So f of P3 came out to, so I just plug this in here, 0.4 something. So in other words, it's positive. So remember, the b's in this case are taking on the positive values. So A3 again remains the same. And sorry, this is A4. We're in step 4. B4 is now negative 1.25. So it's now this new value. Okay, let's take it one step further. Someone could probably do this in their heads, but 1.5. Okay, so 2.75 over 2 over 2. Oh, there it is. Okay. Sorry, I have to type in the right numbers to get the right answer. It works that way. Okay. So our next P, so this is the next iteration, P4 is negative 1.375. So again, we just plug this into our function and we see if it's positive or negative. If you're doing this out by hand, don't do what I'm doing and retype it every time. I would actually just use Sage and then you can punch numbers in if you're fine with that. But right now I'm using Wolfram Alpha, so I have to do it out by hand. So not by hand, but I have to type the whole thing each time. So negative 1.375 squared minus 1.375. Oh, that was supposed to be cubed. Sorry, cubed minus that squared. Okay, so we're getting negative 0.5 approximately. F of P4 is approximately, negative 0.5, and I rounded, but again, we just want positive or negative, don't care. So at this point now, our A moves because A corresponds to the negative function values. So A has finally left its spot. And now A5 is negative 1.375, and B5 is negative 1.25. So that one didn't change. So, because we've run out of space and this is tedious to do by hand, I am going to say, okay, this will be our estimate. So our estimate in this case is negative 1.375 plus negative 1.25. And in this case, I didn't use the other formula that I said would generally give us less rounding error. And that's because I know that in these cases, like all our denominators are essentially powers of 2. So I know we're going to get an exact decimal, and we don't have to worry about rounding in this case. So only because of that. So only because I know we won't get any rounding error or have to worry too much in this case, because we know what the numbers that we started with were, and we just kept bisecting an interval that started with, half numbers. I can just average this and know that it's okay. I'm bad at parentheses. Okay. Over 2. Okay, so this is our root. Our guess for our root is negative 1.3125. So that is our root. And then our error is, well, just half of the length of our previous interval, which is 1.3125. So our error is less than 0.065. The way I calculated that error in this case was I just took this root and I subtracted it from actually either of these endpoints of our final interval. And that gives us the length of the half interval. So error is, I got it by doing either the absolute value of negative 1.375 minus negative 1.3125, running into the other stuff, absolute value, or negative 1.37, no, sorry, using B. Okay. So what I'm doing here is I'm just taking either A or B. I don't care which one, because I know that the root guess is directly between the two of them. And I'm saying my error is equal to, either we can say A5 minus our guess or B5 minus our guess, and it doesn't matter. One will just give us positive, one will just give us negative, but we're taking the absolute value.